Alright, last video of 5.8, comparing integrals, integration problems. So this is example 6. It's in your textbook, page 367. So notice these three integrals look very, very close to one another, right? They all have the square root of x squared minus 1 in the denominator. It's just that what happens with the extra x, or is there an extra x? So in A, there's an extra x in the denominator. In B, there's an extra x in the numerator. In C, there is no extra x. So again, you have to kind of like think through the possibilities, right? And just by glancing at something, you're not going to know immediately what to do. So like in part A, I don't know, to me, it's really hard to not look at that and just immediately see, oh, yeah, inverse trig looks real likely on that. In fact, that looks just like the formula for arcsecant. I mean, like, nothing fancy about it. It just is what it is. Let me redo this as a green. Oh. Okay. So we've been using green for our use. So this looks a lot like arcsecant, because if this is going to be an arcsecant thing, then that's u, and that's a u, right? It has to be the same u. And then du dx is just 1, which that's just a 1, check. It literally is identical to our formula. So if you try to do anything else, if you tried to make x squared minus 1 be your u, your u prime would be 2x. You have an x, but it's in the denominator. You can't have your u prime in the denominator. And you can't force a different degree of x for your u prime. So this is just real straightforward, right? And your a in this case, right, it's like 1 squared, so your a is 1, right? A equals 1. So arcsecant, so we're normally 1 over a is 1 though. Arcsecant u over a, so x over 1 plus c, so just plain old arcsecant x plus c. Okay. B. Now B can't be arcsecant because it doesn't have an x outside the square root. My next thought though, or maybe your next thought would be, well, how about arcsine? My next question would be, well, what sets off alarm bells in your mind that it's doesn't seem like it can be arcsine? What's the ordering of the u squared and the a squared? Right, under the square root, we have essentially a u squared minus a squared, not an a squared minus u squared. For arcsine, you have to have a squared minus u squared, so that's not going to work for arcsine. So your next option is to just come up with a more like generic u and maybe force it to fit some kind of like inverse power rule-y type thing. Now, if it was going to fit a natural log rule, you could have the whole denominator be your u. But again, be careful with that. When you have a square root, also a lot for these, I do remember on previous years, the test, sometimes you see so many square roots in the denominator that you tend to just like zone out and almost like not see it. So make sure you actually realize there's a square root in the denominator. Don't take that for granted. Because if you made your whole denominator equal to u, then you would have your u prime would have to be, right, this weird long chain rule thing, like 1/2 times x squared minus 1 to the power of negative 1/2 times 2x. And compared to that, the only thing you have to contribute to your u prime is an x. Where you're going to come up with all the rest of that stuff, you can't, all right? You'd be totally stuck, all right? So you definitely can't make your u be the entire denominator, but we have some hope for just this part inside being our u, okay? Again, remember back to the days where we could just make the whole thing under the radical be our u, compared to when we did problems like part A, where just the variable part that was squared was our u, putting in inverse trig stuff, right? Remember, you kind of have both options. So here u is x squared minus 1, or du dx. This checks out because the degree of our existing numerator is the same, right? So, right, this is just a constant multiplier of that. Constant multiple off. Multiple different. So we can overcome that. Great. So what do we do to overcome that? So we need to multiply the top by times 2, the outside by 1/2. Okay, now we need to figure out what our outside function is. So our outside function, our outside function, what's being done to our x squared minus 1? What's being done to the x squared minus 1? Well, it's 1 over the square root of that thing. Okay, so you can write it like this. I also would rewrite it like this, -1/2, to remind yourself, oh, it's just actually a power rule thing. Don't get this confused with a natural log thing. The square root changes everything. Antiderivative of this thing. Antiderivative, remember, not derivative. Again, you start doing enough u stuff and you take the derivative of u to fit the form with the u prime that has to cancel, but then you have to find your outside function. You have to take the antiderivative of your outside function to get the indefinite integral, right? There's a lot of moving pieces here. So just be careful. X to the positive 1/2, right? Because you add 1 to the exponent, divide by the new exponent, which is 1/2. Same thing as 2 root x. Okay, so kind of like your final answer is going to have like a 2 times square root of blop in it. And you're also going to have this 1/2, right? So this 1/2, right? This 1/2, it's going to come all the way down here. All the way down here. So this whole thing equals 1/2 times 2 to the square root of blop. What's our blop? Our blop is x squared minus 1. X squared minus 1, all plus c. Again, remember this 2x, right, gets absorbed. That's the u prime. And 2 over 2, that actually ends up canceling. So it's just square root of x squared minus 1 plus c. Pretty elegant. But again, looks completely different than the answer to A. Compare this to arcsecant x plus c, right? One of them is like the square root of a polynomial, and one of them is inverse secant. What? Just by the x being in the numerator instead of the denominator, right? That's why, I don't know, these problems just are so fascinating to me. They look so similar, and their answers just a million miles different. All right, part C. Well, let's see what we can do. Pun. Let's see. My first inclination would be, how about arc sine? But for that, we need a squared minus u squared under the radical. We don't have that. And there's no like fancy way of changing that. Because it's a negative under the radical. If you tried to bring a negative and like factor it out, you'd end up having like some weird square root of -1i thing. We're not doing anything with imaginary numbers in this calculus course. So get that out of your head. You can't end up, like changing around the signs inside the square roots of these problems. So it can't be arc sine. The next thing would be like, well, maybe it's like an arcsecant thing. If it's an arcsecant, remember the arcsecant can be kind of weird. But if it was going to be arcsecant, then your u would have to be x. If our u is x, right? We could try it. Try arcsecant. If so, our u would have to be x. So then our du dx would be 1, which we already have a 1, but we would need an x here. Would need an x in the denominator. And we don't have that, right? Before, sometimes it kind of like, with the weird like e to the x thing, it actually ended up working kind of miraculously because our du dx that we needed in the numerator was like e to the x, and we needed that extra like u outside the square root on the denominator that like also ended up being e to the x, and they actually balance each other out. But here that's not going to work because our u prime is 1, our u is x. 1 over x is not the same. You can't just randomly multiply the whole thing by 1 over x. In fact, you're just trying to force it to look like a. It doesn't look like a. Okay, your other option would be, again, we already tried the whole making the entire denominator u. That u prime is insane. There's no way. You're pulling that out of a hat from starting with a 1 in the numerator. If you made what's under the square root equal to your u, x squared minus 1, your u prime would be 2x. Again, 2x is not a constant multiple compared to 1. There's no way you could just pull that extra x out of thin air. So unfortunately, this is the kind where you actually cannot do this with what you know. Literally, the book says you cannot find this integral using the techniques you've studied so far. Okay, whatever. It says you should scan the list of basic integration rules to verify this conclusion. Okay, that's a dumb thing. So cannot do using Calc 1 techniques. Cannot do using Calc 1 techniques. All right, again, on the AP test and on my tests, you're not going to have this as an answer. So don't try to put this as an answer. It's going to be wrong. But the book is just kind of proving a point, and to prove that there's other kinds of calculus, because you could plot this graph. It's not like the graph of 1 over root x squared minus 1 is like doesn't exist. It's a real graph, which means you can find area between 2 points under the graph, you know. So there is an answer that exists. It's just you don't have the tools to know how to find that answer. Okay, the next one, example 7. Similar idea going on here. Oops, 7. Example 7. Sorry, I'm like breathing on this weird. Okay, so for A, this one has ln's in it. Ln's are always tricky because the derivative of ln x is 1 over x, and so you have x's in the denominator, and you're like confused at which one do you make the u, and ln x dx over x, and c is just ln x dx. Okay, first one. Again, generally speaking, when you see an integral like this that has an ln x in it, and it has just like 1 over, like one other x in the problem, right? Don't get too caught up. Remember that you're looking for a u such that the derivative of that u appears somewhere else in the integrand, right? Remember, the derivative of ln x is 1 over x, not the other way around. Okay, so don't try to choose 1 over x to be your u, because the derivative of 1 over x is actually the same thing as the derivative of x to the negative 1, which is negative x to the negative 2. That has nothing to do with ln x. Okay, so in most of these, ln is going to be your u. Okay, so when in doubt, choose your ln x to be your u. So if your u equals ln x, your du dx is 1 over x, which you already have here, right? There's an implied 1 over x. You already have this, right? So this, now again, we still have to figure out what is our outside function, what's being done to the ln x. Outside function What's being done to the ln x? Well, it's just 1 over ln x, right? Because it's in the denominator. So 1 over x, which is the same thing as x to the negative 1, but actually, so normally I would rewrite it as x to the negative 1, but remember, we're going to be taking the antiderivative of this. The antiderivative of 1 over x is not a power rule thing. In case you ever get in case you were to ever like get confused by that, if you tried to do a power rule on x to the negative 1, right, you would add 1 to the power. So it'd be x to the 0. Already that's weird. Divide by that new exponent, 0. X to the 0 over 0. You got problems, man. That cannot be your answer. We're not breaking math. We're not dividing by 0. So if you ever forget, then if you're consistent, you would divide by 0 and then you'd freak out. Okay, so we're not doing a power rule thing on this. This is going to be your ln blob, right? And again, they love this because now your antiderivative is ln x, and your u, which is completely separate, is your ln x. Remember, we actually did this exact problem like 2 sections ago. They love doing this because it's just such a mind bender, and it's kind of cool. So your overall, right, we don't have any extra thing outside. The 1 over x, remember, goes away because it's our u prime. Our, generally speaking, our antiderivative is just ln of blop. Actually, technically, it is ln absolute value of blop. Let's be more specific. So this whole thing is ln absolute value of blop. What is our blop? Our blop is our ln x. It just so happens to be our blop. It could have been anything, right? If this was like 1, well, no. I guess it was something different. It would have to be something different. But anyways, so our ln x is our blop. Ln x goes in here plus c. We've actually already done this problem. It's weird, but kind of cool. All right, next problem. Again, when in doubt, you're really going to have to choose your u to be an ln x if you also have a 1 over x in the problem, because the derivative ln x is 1 over x. If you chose, say, like x to be your u, well, then your du dx would just be 1. You had no idea what to do with ln x. I don't know what else you could choose. Choosing 1 over x to be your u, that would be weird because then your derivative of 1 over x, your derivative, not antiderivative, your derivative of x to the negative 1 would be negative x to negative 2, which again has nothing to do with ln x. You'd be stuck. You'd have an extra ln x. Can't do anything with that. So you're going to choose ln x to be your u. So u equals ln x. So our du dx is 1 over x, which we already have. Yeah, right? This is like an implied times 1 over x, right? We already have it. Yay! Now again, the kicker here outside is your outside function. What's being done to the ln x? And again, this is like so easy it's hard. Essentially, nothing's being done to the ln x. You're just sitting there in the numerator. So that means f of x, come on, is just equal to x, right? It's not being squared. It's not 1 over that thing, not square rooted. It's just x. So this was actually kind of hard. And so now we're talking the antiderivative. Remember, not the derivative, the antiderivative. Antiderivative of x is x squared over 2. Okay, so generally speaking, our answer, right, we don't have any extra factors or whatever. Again, the 1 over x thing gets reabsorbed into the chain rule form. Generally speaking, our answer is going to be blop squared over 2. What's our blop? Is ln x. So this whole thing, right, it's going to equal ln x, all that blop squared over 2 plus c. That's it. Don't even need any absolute values, because we only need absolute value when it's our antiderivative that's the ln x, not that when it's our u that's the ln x. Okay, looking at C. You have an ln x. First of all, you could rack your brain. Have we learned the antiderivative ln x? We did learn the derivative of ln x. The derivative of ln x is 1 over x. Did we learn any derivative formula such that something's derivative is equal to ln x? Well, we've been getting lots of ln answers lately, but those are all antiderivatives. That's when we had like 1 over blop goes to ln absolute value of blop. So we actually have not learned a formula straight up for ln x. Okay, well, if we try to do some kind of u thingamabob, literally the only option would be for your u to be your ln x, but then you'd need your du dx, which is 1 over x. You need an x somewhere. And if you tried to force there to be like an x in the denominator, only you could do would be to multiply the numerator of the integrand by x. Remember, you cannot put anything with x outside the integrand, outside the integral sign. But if I put an x in the numerator, well, then it's just going to be hanging out there. You're not going to be able to substitute it away. So, moral of the story, can't do this. So same thing as this. This is the same as here. Come on. All right. Cannot do. And again, I mean, ln x is like a thing, right? Like with your current knowledge. Yeah, it's not the current knowledge of the world. It's just with Calc 1, essentially, right? Because you know that, right? A log function's kind of like this, right? So if I wanted like the area between whatever, like that and that or something, like you'd have like that, this negative area, that's positive area, right? So like an answer should exist. You just don't know how to do it. That's it. Okay, now take a look with me. I think I'm going to mostly just talk about this. So again, I'm going to risk it, I guess, but hopefully people have textbooks because I don't want to rewrite all of this. I'm going to talk through your homework problems number 55, 56, 57. I'm going to skip 58 and then 59. I'll write down what I'm doing in here just so that you can kind of see when you're scrolling through the video what this is. Homework problems number 55 to 57 and 59, right? See textbook. Fun fact that's like super cute. My husband and Annalise and Levi, they're 4 and 2. They're having a little camp out on our back porch right now in a tent, in like a real tent, and I bought them like sleeping bags, and they got little lanterns for Christmas. They're all just like sleeping so peacefully. Mommy is very pregnant and also hates camping and uncomfortable sleep conditions, so Mommy will not be sleeping with them in the tent. But anyways, I guess that's a little fun fact that I would just chit chat with you about if I was there in person. So I guess it happened like weeks or even more than a month ago, maybe in your world. Anyways, okay, page 368, number 55. Look at it with me, please. Okay, these are very. In fact, are those the same? Oh, they're very similar to example 6. Notice it's in example 6 we just did, it's x squared minus 1 rather than 1 minus x squared. But same thing where we have no x, then we have an x in the numerator and an x in the denominator. And this will be kind of fun for me because I'm not looking at the solution, so I don't even, hopefully Prof 9 doesn't get it wrong. So hopefully you don't get too all secretly or not so secretly judge me as a class for getting it wrong. But let's see what we can do. Let's think through this together. 55a. Well, boom. That's literally just the formula for arcsine. A is 1, u is x, du dx is 1. Got it. Literally, that should just be arcsine x over 1 plus c. That's it. Nothing complicated. B. All right, well, looks like no longer can we use arcsine. Definitely can't use arcsecant. For many reasons. It would be a squared minus u squared, and the x is in the numerator, so can't use arcsecant. All right, the next thing I would try, again, I'm not trying to put square root of 1 minus x squared all in my u. Again, we already talked about what that derivative would be. It's insanely long. There's no way that we're making that fit this form when we only have an x in the numerator. So I'm making my u 1 minus x squared. That seems promising. If I use 1 minus x squared, derivative that's negative 2x. That's a constant multiple of 2 of x, constant multiple of the numerator, which is x. Great. So I just need a negative 2 in the numerator. So that means I need a negative 1/2 outside. So, and what's the outside function? The outside function, what's being done to the 1 minus x squared? Essentially, it's 1 over the square root of that thing, which again is like blop to the negative 1/2. The antiderivative of blop to the negative 1/2 is blop to the positive 1/2 over 1/2. We've seen this pattern a few times, which is equivalent to 2 root square root blop. So we would end up with negative 1/2 all times to another 2 times square root of blop. Our blop is 1 minus x squared plus c, and the negative 1/2. Where's what am I going? The negative 1/2, and we have a 2 multiplied, so it'd just be a negative. The 2's would cancel. Okay, I think I said that all right. C. C's not looking great. It's like trying to be arcsecant, but it's an imitation. It would need to be x squared minus 1 on the bottom. All right. Don't give up that easily, maybe. I don't know. What else could we try? Again, I'm not trying the u to be the whole square root of 1 minus x squared. There's just that u prime that's a lot. All we got to work with is a 1 over x for our u prime, if we chose that. If we chose our u to be 1 minus x squared, our u prime would be negative 2x, like, same thing as part B. But we need the negative 2x to be in the numerator. The x can't be in the denominator. And we can't just like change powers of x. So C is impossible with what we know. Okay, 56. Ooh, this one's tricky. Tricky. All right, let's see if I can figure out this myself. 56. X squared looks like a pretty good u candidate. Du dx would be du dx would be 2x. We don't have that. Is it impossible? I'm thinking it's impossible. I'm going to come back to that. I think there's like one impossible one in each set. So let me make sure that we can do the other two. But I'm thinking that 56a is impossible because we would need some kind of multiple of x outside that thing. Okay. 56b. Again, it seems like x squared is going to be our u. U prime would be 2x. That's fine. We have an x there, so we can do a 2 inside, 1/2 outside. What is our outside function? So what's being done to our x squared? It's e is being raised to the power of that blop. So e to the blop, the antiderivative of e to the blop, still e to the blop. So we got our 1/2 from the outside times our antiderivative e to the blop. Plug in the blop is x squared. So 1/2 e to the x squared plus c. Sounds good? Okay, c. Again, it's going to look like that power of e is going to have to be our u. Otherwise, if our 1 over x squared was our u prime would have nothing to do with e, and we'd have a e just sitting there. All right, so if our u is 1 over x, derivative of that, remember that's the same thing as x to the negative 1 power. Derivative of x to the negative 1 power is negative 1 over x squared, or negative x to the negative 2, which is the same thing as negative 1 over x squared. Well, we're in luck. We have a positive 1 over x squared. So all we got to do, multiply that integrand by negative 1, multiply outside by negative 1. Again, our outside function, what's being done to the 1 over x? E is being raised to that thing. Outside function is e to the blop. Antiderivative of e to the blop is e to the blop. We got our negative from the outside of the integrands. We got negative e to the blop. Plug in our blop is 1 over x. So negative e to the power of 1 over x, all plus c. Sounds good? Yeah, so I'm pretty confident 56a is can't do with what we know kind of deal. On a lot of these, it's almost like the simpler they are, the more likely it is that you can't do them. But again, just remember, these are the only ones that your answer could be that you can't do them. If they're specifically saying, yeah, set up like this. I'm not giving you ones that you can't do on tests and stuff. 57. Okay. Huh. 57. Let's see. All right. 57a. Normally, like, if it was based on what I said before, it would be like, oh, well, the simpler, the more likely it is that you can't do it. But in this case, if I make u equal x minus 1, u prime, or du dx, whatever, is 1. We already have a 1. Great. So even though it's a reverse chain rule thing, it's one of those like chain rules where the derivative of the inside's 1. So it's like chain rule, schmain rule, I don't know. I don't know. So you actually already have the u prime sitting there. What's being done to your u? It's just being square rooted. So it's like blop to the 1/2. Antiderivative, remember we're doing antiderivative still. Antiderivative of blop to the 1/2 is blop to the 3/2 over 3/2, aka 2/3 blop to the 3/2. Right? We don't have anything outside the integral that we had to change. So we just have 2/3 times blop to the 3/2. So 2/3 times x minus 1 to the power of 3/2 plus c. All right. B. B might be possible. I think B would be something I would have to work out. Let me see. D7B. This looks like one you might be able to do u substitution on. Like formal u substitution. Right, because on first inspection you can't do it just by fitting the form, because if you tried to make this your u, then your du dx would be 1. Whoops. Right, so these are not constant multiples. Right, so can't just fit the form. Can't just fit the form, meaning if something's going to work, it's going to have to be formal u substitution. Okay, but maybe formal u, or don't forget formal u substitution. It might still be possible, because if u equals x minus 1, that means x equals u plus 1, right? You just do a little like plus 1, right? X equals u plus 1. Okay, and this leads to us concluding that du is equal to dx. So if we want to substitute everything out from this problem, so integral x is equivalent to u plus 1. That looks like a 4. No, stop. U. Okay. I don't know why there's a blue box there. U plus 1 times the square root of u times du, because dx is equal to du, we just said. Okay, so if we do that, yeah, this seems like this is going to work out. So again, I don't know why that thing is selected. It's like very strange. Hello. All right, well, I tried. If you distribute that square root u to the other things, right, you're going to get u, u to the 3/2 plus u to the 1/2 du. Remember, we can go ahead and do the integral, but then we're going to plug back in x at the end. So u to the 3/2 goes to u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c. But then we got to plug back in u. Our u was x minus 1. So x minus 1 to the 5/2, come on. Over 5/2, so I'm going to say times 2/5. Plus 2/3 x minus 1 to the 3/2 plus c. All right, so kind of gross, but we just needed formal u substitution. It wasn't impossible. So remember, that is a possibility, especially in problems that kind of look like this. Okay, so B was possible. C, I don't know. 57C. 57C. Again, we can't force it because if our x minus 1 was our u prime would be 1, but we have an x. Can't do that. If we try to do, I would say let's try to do the same u substitution from B. Let's see if we can come up with something. If not, then that's pretty much our only resort. So if we use u substitution from B, u equals x minus 1. So whatever, I'll just rewrite it. For u is x minus 1. So x is u plus 1. Oh no. I hear my son crying outside. Oh man. Okay, so then our du dx was 1, so our du equals our dx. Okay, so if we rewrite this, using all this u substitution, our x is equal to, u plus 1 over square root of u. This is promising. Our dx is equal to du. So we can distribute this, distribute that. All right, this looks doable. So this would be u to the 1/2 plus u to the negative 1/2 du. So this would be integer of u to the 1/2 is u to the 3/2 over 3/2 plus u to the 1/2 over 1/2 plus c. Back substitute. Our u was x minus 1. So 2/3 x minus 1 to the 3/2 plus 2x minus 1 to the 1/2, or you could just be fancier and I think he's going to get a trip back to inside world. He's crying in the tent. Okay, so that works with U substitution too. 59. And let's see. 5. I see. Okay, then 59. It's the other one we wanted to talk about. By we, I mean me. Oh, come now. So, 59. Homework 59, decide whether you can find this integral. This one is kind of tricky. I was just thinking through the options, and I did have a moment of, well, doubting the answer. All right, so places that your mind should go to. First of all, if you made what's under the square root to be u, so u is x squared plus 4, u prime would be 2x. Again, you don't have an x, you can't magically make up an x. It's not going to work. Probably the other thing that's coming up in your mind, that came up in my mind, is how about arctan? If this was an arctan problem, right, remember when we do arctrig, that kind of takes away the burden of, right here, if this was arctan, our u would be x, because it's like u squared plus a squared, which means our u prime would just be 1, and that 2 wouldn't be a problem. And so those are the thoughts I actually just had. But here's the thing, and again, this is what I just actually warned you about. So you see so many of these that you kind of almost, they blend into the background. What's wrong? Hopefully someone already knows. That's square root. There's a square root there. See, you probably weren't even thinking about that. You were so focused on, oh yeah, x squared plus 2 squared, and yeah, it looks like arctan. Well, it's not arctan if there's a square root. Remember, arcsine and arcsecant have square roots. Arctan does not have a square root. That cannot be arctan. So, no, it can't be, right? I mean, I kind of just explained the reasoning. You can say, so no, this is impossible because it can't be arctan because of the square root. You cannot equal x squared plus 4 because the numerator is not a constant multiple of x. That's it. Okay. Good luck on your, again, quiz test. I forget what it is. Wrapping up chapter 5. Again, I think I said in the notes, this quiz test, whatever it is 10 integrals. Well, one's like kind of integral. It has to do with an integral. And it's just like pure, like, do the problem. There's no like, context or word problems or whatever. So it's probably my favorite one. Maybe probably in all the math classes I teach. So I hope you have fun with it. I will see you when I make a video about chapter 6. For chapter 6, we're only doing 6, 1, 2, and 3, and a lot of it I think you can read and kind of understand yourself. So I think I'm just gonna have one video about it, and yeah, hopefully that will be enough to get you through until I rejoin you after my maternity leave. All right, hope you're doing well. God bless.